In this video, we're looking at lesson 2.1, and we're continuing on from where Mr. Nichols left off. We're primarily focusing on transformations. So we're going to look at how to transform data and how to also describe density curves for it. So before we begin with transformations, just kind of look at this scenario. Now it's on this light bluish slide, so it's not in your notes, but it's something for you to think about before we get into it is, if there was a recent quiz given, and the teacher had two options. They could either add 10 points or increase everyone's score by 10 percentage points. Now what that means, it doesn't mean add 10%. It means if someone got an 80% on the test, they would find 10% of 80, which would be 8, and add that on to it. And so they're really increasing it by multiplying by 1.10. That's what that part means. And the questions we have to keep in our mind and just think about is, how would each of those affect certain parts of the distribution? How would it affect the shape? If I increase, and just by adding 10 points to everybody's score, how would that affect the shape? How would it affect the mean, the median, the measures of center? How would it affect the measures of location, the first quartile, the third quartile? How would it affect the IQR or standard deviation or other measures of spread? So we're going to kind of think about that. And if you look at this, a quick example, here's some test scores. And just kind of think about it. You can see the numbers, and if you were to kind of imagine, I put them in least to greatest order for us, you can see really, for the most part, where the median is. And if I just said, you know what, if this was out of 100 points, so I'm looking at this as total points, and I decided to add 10 points to everybody, and I just keep that up. Don't worry, you're not going to see me do it all the way across, but I keep it up, and I have 99. This person got it perfect. This person showed that person up. And so if I do that, how would that affect the shape, the measures of center? How would that affect the spread if I just add the same number to all of those? That's what the previous slide was talking about. But what if I decide to, say, increase by 10%? So take 10% of the number and add to the original. So really multiplying by 1.10. So if I do that to 66, 10% of 66 is 6.6. So that would be 72.6. 10% of 72 is 7.2. So that would be 79.2. 10% of 73 is 7.3, so that'd be 80.3. And again, you're not going to hear me do all the 10% all the way across. I'll even skip the 89. 10% of 90 is 9, so this would be 99. Not quite a perfect. 10% of 93 is 9.3, so that'd be 102.3. How would that affect the measures of center, the measures of spread? And that's what we want you to keep in mind in this lesson. Is we are thinking of it like kind of, you would use the word curving, but these are the two scenarios. You're either going to be adding or subtracting by a number or multiplying by a number. So we're transforming data, and what that does is it converts the original observations from one unit of measurement to a different scale. And you've done this throughout your life. When you convert from feet to inches, when you convert from meters to centimeters, degrees Fahrenheit to degrees Celsius, you are transforming data. And it can affect the shape, the center, and spread of a distribution. The key word is it can. So we're going to have to try and figure out which one affects which. So when you're adding or subtracting a constant, so if you're adding the same value A, whether it's positive, 0, or negative to each observation, what it's going to do is it is going to increase or decrease, depending on what your A value is, the measures of center and location. So your mean, your median, your quartiles, your percentiles, they're just going to shift up. Sorry, I say up. It's going to shift and be added by that. It will not affect, it does not change the shape of this distribution or the measures of spread. The range, the IQR, the standard deviation, those stay the same. And the reason why is because if I had, like I said, a 66, all I'm doing is I'm adding 10 points to each of these. 72, I'm adding 10 points to it. So add 10 and I'm going to get 82. So all that is doing is kind of really like a horizontal shift. You think of it graphically on it to the right 10 units. So the mean's going to increase by 10, the median's going to increase by 10, quartiles, percentiles are going to change, but it's not going to change the shape of it. It's not going to change the range. So adding or subtracting by a constant is going to affect the measures of center and location. So here's an example. So 30 test scores, maximum score of the test was 50 points. So suppose the teacher was nice and added 5 points to each test score. Would that change how would that change the shape, the center, and spread of the distribution? So you see we have two dot plots. The top one is the original score. The bottom one is score plus 5. And we just take a look at it. And you can kind of see how this shape is still the same down below it. And let's see if I can get that to work. So if I can take a look at it, and I'm going to try my best to highlight. So I think I got all the points. I'm going to hit copy. I'm going to paste the image. So here's the original. You can kind of see them overlapping for the most part. And then if I come down here, you can see the shape is the exact same of them. So we have that. Get rid of that now. The shape is the exact same. The only difference is the measures of center, the mean, the median shifted up. Measure the location shifted up. The spread didn't change. It was the same shape. So here we want to go is, here's a summary table. One, the sample size, n, is going to stay the same. We know that. Everyone's score was increased by 5 points. So that should mean that my sample mean is going to increase by 5 points. Anything dealing with the actual value of it, the measures of location on it, is going to increase by 5. So this should increase. My minimum number should now be 17. If someone got 12 on that test, 12%, they're not going to have a 17%. This person is going to have a 37. This person is going to have a 42, the answer to life, universe, and everything. And then this person is going to have 46. This person is going to have 53. So if I take a look, that's pretty good. It stayed there. Now we're going to figure out what the other ones are, but those are consistent because I'm just adding 5 points. Well, how is that going to affect spread? Well, we said the shape's the exact same. And in that case, then all it's doing is shifting left to right. I'm going to take a guess. I'm thinking that my standard deviation is going to be the same because the shape is generally the same. And it's not stretched out at all. I mean, it was the same image left to right. I'm going to say my IQR is still 9 because everything increased by 5 points. So everything got that same shift. I'm going to say my range is still 36. And so if we take a look, here's what we have. We had sample size of 30. Let's see, we added 5 here. We did add 5 here, here, here. Good. And I said that these numbers would stay the same on it. So shape, no change. Measures of center and location, they increased by 5. Spread, no change. And if you look at how I highlighted it, the measures of center and location I kind of underlined in blue. The ones I highlighted in green are your measures of spread, standard deviation of the sample, IQR, and range. And so adding, here's your setup. It's not going to change shape. It's not going to change spread. It will increase by A or decrease by A if you're subtracting to the measures of center and location. So that is transforming data by adding and subtracting. Now when you're multiplying or even dividing on it, each observation by the same number B, whether it's positive, negative, or 0, what it's going to do is it's going to multiply the measures of center and location by B. It is going to multiply the measures of spread by the absolute value of B. And that's kind of important to keep in mind. For this one, it's going to be measured, the spread is going to be multiplied by the absolute value of B. It will not change the shape of the distribution. So we can see multiplication based off of this is going to change center, location, spread. it will not change shape. And so let's take a look at this one. Same idea. Suppose that the teacher in the previous example wanted to convert the original test scores to percents. So the test was out of 50 points. So by multiplying by 2 to make it out of 100, easier to put in the grade book, how would this change the shape of the center spread? So you can see the two dot plots. And notice, I mean, here's the original, just like before. There's the original. Now, if I take that and just, hey, I'm going to put it down here right below it, it looks like it's stretched out. I mean, right here is the original point. It's not even close to being the same spread on this. I mean, this one's way stretched out over here for it. So, it got stretched out. So that's really nice to know. But did it change, even though it got stretched, did it change its shape? Well, if I look at the general shape, no. It just pulled it to the left, pulled it to the right, stretched it out that way. So if I'm looking at this, let me think for a minute on what's going to happen. My sample size, that of course is going to stay the same. There's still 30 students who took it. But my sample mean was 35.8. And it got scaled by multiplying by 2. And so that's what happened. This person decided, hey, they're going to multiply this teacher each number by 2 to make it 100. So, if my sample mean was 35.8, I'm going to say it's going to be now 71.6 because I'm doubling the numbers. And so I'm going to kind of stick with the same way I did it before. The person who got 12 out of 50, they would get 24%. The person who got 32 out of 50, they get multiplied by 2, 64 out of 100. This would be 74 out of 100. This would be 82 out of 100. This would be 96 out of 100. And so that's really those. And I'm sticking with kind of leaving these alone right now and trying to think more about this. Well, I've said it's stretched it out. It's kept the same shape. I'm going to go ahead and make a guess that the shape is still going to remain the same on it. It's more stretched out. But standard deviation, let's IQR and range, but let's look at range. Look at this, from here to here, and I can even just draw and connect those. If I look at that, if that's the range, there is no way that it has the same range on it. Doesn't even look close to it. I'm thinking that range is going to be multiplied by 2 as well for it. So I'm thinking this is going to be 72 for that. And if I'm stretching out and I think about, maybe a box plot on this, I'm thinking the IQR is going to be multiplied by 2 as well. And the standard deviation, so let's say 16.34. So there's my guessing. I think everything's going to be multiplied by that 2 for measures of center, measures of location, and measures of spread. But I'm thinking the shape's going to stay the same. So it says double, which, that's multiplying by 2. And I believe all my answers were right. You do have 24, 64, 74, 82, 96, 18, 72. So when you are transforming by multiplying, what does that mean? Shape doesn't change. Measures of center, location will get multiplied by that number. Measures of spread will get multiplied by the number. So there we have transforming data by multiplying and dividing on it. And we do it for adding and subtracting. Shape doesn't change, so if I can kind of zoom out and look at them both, is we have shape does not change for adding and subtracting. Shape does not change for multiplying and dividing. Ooh, there's something very constant. If you're adding, it's going to increase by that value or decrease by that value if you're subtracting. If you're multiplying, it's going to do that for the centers as well. Spread does not change when it comes to adding or subtracting, but it does change for multiplying because you're stretching it out. Now, we can, again, blue slide means it's not on there. We can start looking at maybe a combination of them. And if we do kind of an operation on it, you can have a new variable, we'll call it x sub nu, given by the equation x sub nu equals a plus bx. A is the constant that is being added or subtracted to each number. B is what's being multiplied. For example, a scale is measuring everyone's weight to be 3 pounds more than their actual weight. To correct this, the person recording the weights must subtract 3 pounds from each person's weight. So if they're subtracting, how is that going to affect the mean, the median, the quartiles, the location, or other measures of location? Well, again, it's going to, if you're subtracting from everybody, everyone is going to lose 3 pounds from what's on the scale. So you're subtracting 3 from the mean, from the median, from the quartiles. So measure the location, you're going to subtract 3. The standard deviation, well, if everybody shares that same subtraction, they all keep the same position, just 3 to the left. It's not going to affect the measures of spread like standard deviation or IQR. And that is a bell. If we have linear transformations in this case, what if everyone's weight is 5% less than their actual weight? So to correct this, the person recording must increase each person's weight by measurement of 5%. Well, that means they're multiplying by 1.05. Well, then you're going to do that to the mean, the median, the quartiles, and other location. You're going to multiply it by that 1.05. And that is a stretch on it. And so you're going to multiply also these measures of spread by 1.05. And so one thing that is very common on how that is used is if you're looking at it with converting from either Celsius to degrees or from degrees Fahrenheit or Fahrenheit to Celsius, it's that formula on it. And so if I take a look, if I'm converting from Fahrenheit to Celsius, here is the formula. You take 5/9 times Fahrenheit minus 32. Now, to make it easier, we just distributed it and got 5/9 F minus 160 over 9. So what effect is this going to have on the measures of location, or measures of center, of mean, and median? And so we have this, the mean and median and all other measures of location are going to be multiplied by 5/9. And then they will be subtracted by 1/69. So I want to kind of highlight that. So the measure of location will be multiplied by 5/9. Well, look at that. You're taking each degree of Fahrenheit and you're multiplying by 5/9. And then, I like the word then it will be subtracted by 1/69. That's just order of operations, people. What effect is this going to have on the standard deviation and the IQR? Well, the measures of spread will change. And the way that they're going to change, if you look at the two highlighting, the green and the orange, is subtracting or adding does not change measures of spread. And that's what we have to keep in mind, is measures of spread are not affected by adding or subtracting, but they are affected by multiplying. So all measures of spread will be multiplied by 5/9, but the negative 1/69 has no impact because measures of spread are not affected by adding or subtracting for it. So what I want to do is I want to kind of connect, final to end this, transformations and z-scores. So the reason why I have this screen right here is to give you a heads up to get your calculator so you can pause the screen, pause the video to get your calculator. What I'm going to do is I'm going to project my computer, hopefully to the iPad on it. There it is. All right, so I have my calculator from the computer on the iPad, and what I'm going to do is I'm going to go to Stat. And just kind of watch. What I did was I added, and I'll get rid of that column, put all those original percents from that blue slide at the beginning of the video in here. And if I were to hit zoom 9, I have it set on histogram. What I want you to see is that's the histogram of these tests. And I'm going to hit Command T, kind of take a screen capture of it, and I'm going to put that screen capture, let's put it up here, just to come back to it later. All right, so what I'm going to do is I'm going to do a transformation. I'm going to go to my Stat, Edit, and I want to use the z-score formula that Mr. Nichols taught you in the other video. And the z-score formula in the other video is take your statistic, which is all the values in L1. So I'm going to hit parentheses, I'm going to go L1, and you want to find its distance from the mean. So I'm going to go minus, I'm going to hit second list, go over to math, and I want the distance from the mean. So I'm going to find the mean of L1. And I want to divide by the standard deviation. So I'm going to go to second list again of that statistic. So boom. So standard deviation of L1. Now this, by the way, is the formula for z-scores, just using these lists. It is your statistic minus the mean over the standard deviation, and I'm hit enter. And what that did was it found all the z-scores for that list. So if I do 66 minus my mean divided by the standard deviation, I would have a z-score of negative 2.266. So it's doing what Mr. Nichols did in the previous thing, but I want to show you something. Is we see the original histogram right there. What I want to do is I want to turn off plot 1. And I think I have plot 2 turned on. And on my plot 2, this time I made my list for that histogram L2. And I'm going to hit zoom 9. That is the histogram of the z-scores. So I'm going to hit T, and we can see them both together now. Did it change anything? Look at the original. All it did was it standardized it. It shifted that histogram to the left, and then it scaled everything by the standard deviation. The z-score formula is a transformation. What it does is it takes all the values, and you can see the blue histogram, and moved them to, I'd say the y-axis, there's 2, 0 on the x. It tries to standardize everything so you could be most of the data, let's say about 99.7% of the data between -3 to 3 standard deviations from the mean. And that's what it tried to do, is it shifted it over here, and then it scaled it. So here's 1 standard deviation, here's 2 standard deviation, here's 3 standard deviation. It's trying to scale it that way for us. So everything that we're dealing with z-scores can kind of relate to something that is centered around the, I'd say, origin of it around 0 on that horizontal axis. So that is how the two relate to each other on it. It's just something interesting to realize that your formula for a z-score is similar to what we've been doing. You are taking z equals x minus x bar over, in this case, let's just say sample standard deviation. You are performing a transformation on it. I want you to realize that. You are subtracting, and then you are scaling that number. You are dividing by something. You are doing a transformation for it. So next up, we have density curves. In chapter 1, we developed a kit of graphical numerical tools for describing distributions, SOCs. Always plot your data, make a graph. Look for the overall shape, center spread, and any departures like outliers. Sometimes the overall pattern of a large number of observations is so regular we can describe it by a smooth curve. So you see that on the bottom right, you have a histogram, and you can see the red curve. A density curve is a curve that is always on or above the horizontal axis, and it has an area of exactly 1. And the reason why is you can think about probability as we get there. You know, the area is going to always be, the highest probability is going to be 100%. All probabilities should add up to the 100%. It describes the overall pattern of the observation. The area under the curve and above any interval values on the horizontal axis is the proportion of all observations that fall in that interval. So some common looking histograms that can be described with a smooth curve. You have symmetric, unimodal, kind of bell shaped there. You have skewed left, you have skewed right, and you kind of see how I can sketch a curve to describe all of those. You have a uniform, and by the way, even though it's not quite curved, you can have a uniform. You have bimodal, so I have a little curve, there's 2 modes. And you have multimodal. And right here is a good example of uniform, ba-boom, 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 on it. The total area under the curve is 1. So here's a uniform, here's a bimodal again, here's skewed, here's approximately normal, and that's a very special density curve we're going to get really used to. 1 standard deviation. And the question is this a density curve? Just because it's on the x-axis doesn't guarantee it. If I try, the idea is the area should equal 1. And if you find the area of, and you do this with a triangle and a rectangle, could have done a trapezoid, it adds up to 0.96, so it's not a legitimate density curve. So don't just think anything that is drawn on the horizontal axis is going to be a density curve. It has to have an area of 1 to be legitimate. So we can have some alternate examples. Let's go on. So when describing density curves, The median of a density curve is the equal areas point. And this I talked about in a previous video. Is this going to cut the area in half perfectly? Half the data to the left, half the data to the right. That's what a median is. The mean is the balance point at which the curve would balance if it was made out of solid material. The mean and median are the same for the symmetric density of the curve. They both lie at the center of the curve. The mean of a skewed curve is pulled away in the median in the direction of the long tail. Not all the way over to the tail, but it's going to be pulled a little bit from the median. It's going to go through it. So we have equal area here, equal area here. That's median. If you were to balance it, and you can look at the red, it's kind of like a little pivot, it would balance it perfectly. So this would be 50% of the area to the left of that, and to the right of the blue line would be 50% of the area as well. That is 2-1. That is really what our main idea behind it was. Hopefully you can understand transformations, and hopefully you enjoy